all, I'm going to be working through this worksheet solving radical equations and inequalities along with some book problems for some extra examples. So you can follow along, take notes if you like. You'll also get this worksheet in class, and hopefully this works out. Okay, let's get started. Number one, the speed s in miles per hour that a car is traveling when it goes into a skid can be estimated by using the formula s equals the square root of 30 times f times d, where f is the coefficient of friction, d is the length of the skid marks in feet. A car skids to a stop on a street with a speed limit of 30 miles per hour. The skid marks measure 35 feet and the coefficient of friction was 0.7. Was the car speeding? Okay, so let's take this information and just plug it in. That's all that this really is asking. The speed limit's 30 miles per hour. That doesn't go into the equation, but everything else will. So we have s equals the square root of 30 times f, which is the coefficient of friction, which here is 0.7, times d, which is the length. So we have a length of 35 feet, so times 35. So that equals the square root, square root of 735. So that's about equal to 27.11. So if that's the speed, which is what s stands for, and the speed limit was 30, then no, the car was not speeding. In fact, it was going about 3 miles per hour less than the speed limit. Okay, let's go on to the next one. Okay, the time t in seconds that a car takes to travel a quarter mile when starting from a full stop can be estimated by using the formula t equals 5.825 times the cube root of w over p, where w is the weight of the car in pounds and p is the power delivered by the engine in horsepower. If the quarter mile time for a 3,590-pound car is 13.4 seconds, how much power does its engine deliver to the nearest horsepower? So let's just plug in the information that we know. So we have t equals 5.825 times the cube root of, okay, we know the weight is 3,590, so we're going to put 3,590 over, P is the horsepower, and that's what we're solving for. Oh, and the T, we know that is 13.4 seconds. So now we can solve for P. So I'm going to start out by dividing both sides by 5.825. So 13.4 divided by 5.825 is 2.30. And then now I'm also going to take this cube root and I'm going to split it into two separate cube roots. So I have the cube root of 3,590 over the cube root of P. So here, if I multiply both sides by the cube root of P and then divide by 2.30, I'll get the cube root of P equals the cube root of 3,590 divided by 2.3. Okay. But I want to get P by itself, so I'm going to cube both sides. So here, the cube root of P cubed is just P, and then the cube root of 3,590 cubed is 3,590, and 2.3 cubed is 12.167. 167. So then P, that's about equal, let's see, that's equal to 295.06. So to the nearest horsepower, That is a horsepower of 295. Okay, let's look at number 3. The formula S equals the square root of 21 times D relates a stunt car's speed S in miles per hour at the beginning of a skid to the length D of the skid in feet. A stunt driver must skid her car to a stop just in front of a wall. When the driver starts her skid, she's traveling at 64 miles per hour. The driver is 200 feet from the wall when she starts her skid. How many feet will be between her and the wall when the driver comes to a stop? Round answers to the nearest foot. Okay. So if we have, let's draw a picture. There's the wall, and the car is here. Isn't that cute? Okay. And it's driving along, and she starts out 200 feet from the wall, and she stops just before it. We're trying to figure out how much distance is between her and the wall when she stops. So the length of the skid is going to be 200, because that's how far she's starting away from the wall, minus x. So that's just this part right here. So 200 represents the whole thing, but the skid is only this part right here. So if we take out the x, that will leave us with the length of the skid. So let's start plugging into the formula. So we have S equals the square root of 21 times D. So the S stands for the car's speed in miles per hour, which was 64. 21. And then the length of the skid is 200 minus x. Okay, so I'm going to multiply the 21 times the 200 minus x. So I get 64 equals the square root of 4,200 minus 21x. Now I'm trying to solve for x, which is the length of the car from the wall when she stops. So I need to square both sides. So now I'll have 4,096 equals, the square root cancels with the square, so I have 4,200 minus 21x. Okay, so then if I just solve for x here, I'll start out by subtracting the 4,200 from both sides. Get negative 104 equals negative 21x. So then if I divide both sides by negative 21, I get x equals 4.952. So to the nearest foot means that it was, we'll just round that up to 5. So she stopped 5 feet in front of the wall. Okay, number 4. The diameter d in inches of a rope needed to lift a weight of W tons is given by the formula d equals the square root of 15W over pi. How much weight can be lifted with a rope with a diameter of 1.5 inches? Okay, so 1.5 is the diameter, which is what d is equal to. So we'll have 1.5 equals the square root of 15. We're looking for the weight divided by pi. So to solve for W, I'm going to start out by multiplying both sides by pi. So I get 1.5 pi equals the square root of 15W. Now I'm going to square both sides. Make sure you're squaring the whole thing and distributing the square to both parts. So that way you get 2.25 pi squared equals 15 times W. And then we'll divide both sides by 15 to get W by itself. So Whenever I evaluate this 2.25 pi squared divided by 15, I'll get W is equal to 0.15 pi squared. So putting that into just a number without pi, I'll get a W of about 1.48 tons. And there's your answer. Not so bad. Okay, so that's the end of the worksheet part of this. And then at the end of the worksheet that you'll get, you'll see that there will be 3 sections of book pages. Here's the first one, and I'm going to work these 6 problems with you for some additional examples. Okay, so we're given a table of values here that describe the damage level, category number, and the minimum wind velocity of tornadoes and how we can categorize them. The equation V equals K times F plus 2 to the 3 halves can be used to determine a tornado's minimum wind speed velocity V in miles per hour, where K is a constant and F is the tornado's category number on this scale. So we have 3 parts to solve here. Based on the information in the table, what is the value of the constant K? So what we can do is just take one of these rows. Let's just use the first one, I guess. And we're going to solve for what K is equal to. Okay. So if my function V equals K times F plus 2 to the 3 halves, okay, is what we're going to use. So I will take a velocity of 73 equals K, what I'm solving for, times our category number for 73 miles per hour is 1. And we'll add 2 to that and raise it to the 3 halves power. Okay, so we'll have 73 equals K times, this is 3 raised to the 3 halves power, so you take the square root of it and cube it, and you'll get 5.196. So we're multiplying by. So then to divide both sides by 5.196, we'll get K equals 14.05. So it's pretty close to 14, so we'll say that K is about equal to 14. So there's our constant. Okay, so for part B, what would be the minimum wind velocity of an F6 tornado? So now that we know what K is, we can use that in our function again. So we're looking for the minimum wind velocity of an F6. So we're solving for V. K is equal to 14. We solved for that already. We have a scale of 6. Then we'll add 2, raise it to the 3 halves power. So we have 8 to the 3 halves times 14. And that's about 317 miles per hour. And for that part, you can just type that into the calculator. And then for part C, winds on Neptune can reach velocities of more than 600 miles per hour. Use this equation to find the categories. So if we have C is going to be, plug in the related information. So the velocity is 600. We know that K is 14. We're looking for the category number. We're going to add 2 raised to the 3 halves. So I'll start out by dividing both sides by 14. I get 42.86 equals F plus 2 to the 3 halves. I want to get rid of that exponent, so I can multiply that by 2/3, and that will cancel out. So I raise each side to an exponent of 2/3. So over there we're left with the F plus 2. And 42.86 raised to the 2/3 power is 12.25. 12.25 Now I can subtract 2, so I get 10.25. So we'll just go to the nearest category number. So that would be, on Neptune, that's 600 miles per hour, an F10. Just rounded that 10.25 down. Okay, number 51 on page 633. For a spinning amusement park ride, the velocity v in meters per second of a car moving around a curve with a radius r meters is given by v equals the square root of a times r, where a is the car's acceleration in meters per second squared. So A, for safety reasons, a ride has a maximum acceleration of 39.2 meters per second squared. If the cars on the ride have a velocity of 14 meters per second, what is the smallest radius that any curve on the ride may have? Okay, so let's start setting up our function here, our equation. So we have part A is v equals the square root of a times r. Okay, so our velocity is 14 equals the square root of our acceleration is 39.2, and we're solving for r. So to get rid of the square root, we'll square both sides. 14 squared is 196, so now we'll have 39.2 times r, and then we'll just divide both sides by 39.2, and we'll get r is about 5 meters. So 5 meters, that's the smallest radius that any curve on the ride may have. Okay, and then part B. What is the acceleration of a car moving at 8 meters per second around a curve with a radius of 2.5? So this time we're going to solve for A. So the velocity is 8 equals, we're solving for the acceleration, and the radius is 2.5. So again, we want to square both sides. So we get 64 equals, now it's just 2.5 times a. The square root canceled with the square. Divide both sides by 2.5 and we get a equals 25.6 meters per second squared. Okay, now let's look at number 52. The time t in seconds for a pendulum to complete one back and forth swing is given by t equals 2 pi times the square root of L over 9.8, where L is the length of the pendulum in meters. So part A, find the length of a pendulum that completes one back and forth swing in 2.2 seconds. Round to the nearest hundredths of a meter. So here we go. So for A, again, we're starting out with that equation. And we're going to fill in the related information. We're finding the length, so we're solving for L, but we're given T, which is 2.2. And now we just get L by itself. So I can start out by dividing both sides by 2 pi. I'm going to go ahead and make that into a decimal. So when I divide 2.2 divided by 2 pi, I get 0.3501. We'll keep a few extra decimal places for a little bit. Equals the square root of L over 9.8. I'm going to square both sides. So this will be 0.1226 equals the square root and the square cancel, so I'm left with L over 9.8. So then when I multiply both sides by 9.8, I get L equals 1.20, just to the nearest hundredth, and that's in meters. So there's the answer to part A. So a pendulum of 1.2 meters will take 2.2 seconds to complete one back and forth swing. Now we have part B. A clockmaker needs a pendulum that will complete 120 back and forth swings in 1 minute. To the nearest hundredth of a meter, how long should the pendulum be? So if we go back and forth 120 times in 1 minute, that means for one swing, it takes half of a second. So 0.5 seconds. So now we're still solving for length again. Oops. Okay. So I'll start out by dividing by 2 pi. So I get 0.78 equals the square root of L over 9.8. Square both sides to cancel out that square root. So now I have 0.006 equals L over 9.8. Then multiply both sides by 9.8. So that's 0.062. But I want to get it to the nearest hundredth. So that pendulum would need a length of 0.06 meters. All right, number 58. On a clear day, the approximate distance d in miles that a person can see is given by d equals 1.2116 times the square root of h, where h is the person's height in feet above the ocean. So part A, to the nearest tenth of a mile, how far can the captain on the clipper ship see? Okay, so let's start this out by plugging in the information we know. So the captain is, in this picture here, he's 15 feet above the ocean. So we'll have D equals 1.2116 times the square root of the height above the ocean, which is 15. So then that is D equals 4.7, and that's in miles. So you can see 4.7 miles. Part B is how much farther to the nearest tenth of a mile will the sailor be able to see than the captain? The sailor's all the way up here. He's 120 feet above the ocean. So first let's find out how far he can see. So we have D equals 1.2116 times the square root of 120. So he can see 13.3 miles. So if we take what he can see and subtract what the captain can see, he's seeing 8.6 miles farther. And then now for part C. A pirate ship, is approaching the clipper ship at a relative speed of 10 miles per hour. Approximately how many minutes sooner will the sailor be able to see the pirate ship than will the captain? Well, we know that the sailor can see 8.6 miles farther. So then if we're seeing 8.6 miles farther, and the ship is coming in at 10 miles per hour, the miles unit will cancel. So we're just left with these hours here, and the hours are going to be the units. So I have 8.6 divided by 10 is 0.86 hours. But it asked how many minutes, so we need to change this into minutes, so we'll multiply it by 60, so we'll get 52 minutes. So the sailor will see the pirate ship 52 minutes before the captain. Hopefully he tells the captain to give him a heads up so they can get out of there, because we all know pirates, those are no good. Okay, next problem. So number 59, the formula S equals the cube root of m over p relates the side length S of a metal cube to its mass m and its density p. The density of a gold is 9.3 grams per centimeter cubed, and the density of lead is 11.34 grams per centimeter cubed. cube centimeters. How much greater is the mass of a cube of gold than the mass of a cube of lead if both cubes have a side length of 5 centimeters? So for gold, write it in yellow. It's really hard to see. Okay. So for gold, when we use this formula here, S, the side length for both of these is 5. So we'll have the cube root of. We're solving for the mass over the density, which for gold is 19.30. Okay, so if we're solving for this, I'm going to split this into two separate cube roots. So I have 5 equals the cube root of m over the cube root of 19.30. So I multiply both sides by the cube root of 19.30. I'll get 13.41 equals the cube root of m. You could have also just went ahead and cubed both sides. Maybe that would have been easier. Could have done that, but just to show you, you can split it and then multiply and then cube, or you can cube right away and then multiply. It goes either way. Okay, now I'll cube both sides. So that will give me a mass of 2412.5 grams. Whereas the lead has, again, a side length of 5. We're looking for the mass. Its density is 11.34. So in this one, let's do what I would have done on the other one. So just to show you, we can just go right into cubing both sides. 5 cubed, 5 times 5 times 5 is 125, equals, so you have m over 11.34. So then m, when I multiply both sides, 125 times 11.34 is 1,417.5. So then that tells me how much greater is the mass of a cube of gold than the mass of a cube of lead. So if I just take the difference of these two things, then I will get a difference of 995 grams. And now for the last example. The surface area S of a cone is given by the formula S equals pi times the square root of r squared plus h squared, where r is the radius of the base and h is the height. What is the approximate height of a cone with a surface area of 40 square inches and a base radius of 8 inches? So we take our formula, S equals pi times the square root of r squared plus h squared. S, the surface area, is 40, equals pi times the square root of r squared. So we'll have the radius squared is 64, 8 squared, plus h squared is, and so we're solving for h. So we'll divide both sides by pi. So 40 divided by pi is 12.732 and so on. So now we'll have the square root of 64 plus h squared. Let's get rid of the square root. I'll square both sides. So I'll have 162.114 equals 64 plus h squared. Now I'll subtract 64 from both sides. Go up here with this. So I'll get 98.114. Now when I square root both sides to get rid of that squared, I'll get h equals 9.905. So when I compare that to my answers up here, that's about equal to 10. So B is my answer. Okay, well that's it. I hope these examples will be helpful for you to complete the book problems that you will get in class. And I will see you guys later. Bye!